Welcome back to the Math Professors. We cover topics that can be found in any college math class. I'm Professor Van Hamlin. We're going to cover translations to the s-axis and then solving these differential equations that have this form. So if you like the content, please consider liking, subscribing, and sharing. So the first translation theorem says the Laplace of f of t is equal to f of s, and if a is any real number, then the Laplace of e to the at times f of t is going to be equal to capital F of s minus a, which we can see that this is nothing more than a shift of capital F of s to the right a units. So that's why they call it a translation theorem. So here's kind of the proof. So if I take the Laplace of e to the at times f of t, we know it's the integral from 0 to infinity of e to the minus st times, well, that function I'm trying to find the Laplace of. Now, since these things share the same base, you can combine that base, condense that base, and then write this as this exponent instead, and you can see that this is nothing more than, a translation of s minus a, which is why we get capital F of s minus a. So let's use this theorem to be able to find the Laplace, and then eventually the Laplace inverse, and then we'll take we'll find a solution to a differential equation. So what this e function does is shift capital F over, in this case, it's going to be 6 units. So the idea is if I know the Laplace of t cubed, then I also know the Laplace of e to the 6t times t cubed. Well, Laplace of t cubed is going to be equal to 3 factorial all over t to the fourth, or sorry, s to the fourth. So that means the Laplace of this thing is just going to be this, because remember, this is capital F of s. So this is going to be this capital F of s shifted to the right 6 units. So remember, this represents capital F of s, because this is going to be the Laplace of f of t. So that means for this one, again, it's going to be this function shifted over 6 units. So that means this Laplace is going to be equal to, well, it's going to be 3 factorial all over, shifting this over 6 units is going to be equal to, my goodness, s minus 6 to the 4th power. Now we can, simplify if we want to, 3 factorials, 6, so this is going to be 6 all over s minus 6 to the 4th power. All right, similarly, if I want to do this one, again, it comes down to I know the Laplace of the sine of 3t. If I know the Laplace of the sine of 3t, this is nothing more than a shift, in this case, left 5 units. So its Laplace is going to be equal to, remember that the sine function is going to be s squared on the bottom plus, this 3 squared, all over, the square root of the 9, which is going to be 3. So now what I have to do is I'm going to have to shift this thing over, left 5 units. So that means this is going to be equal to 3 all over. Now our s is now going to be replaced with, really what I'm doing is I'm going to evaluate this at s minus 6. S plus 5. I have to shift this over 5 units. So this is now going to be equal to s plus 5 squared plus 9. So again, it's nothing more than a shift of this known Laplace. Similarly, we know that the Laplace of the cosine of 7t is going to be equal to s all over s squared plus 49. So for me to find the Laplace of this is nothing more than a shift to the right 2 units. So what I'm going to do is I'm going to evaluate this at s minus 2. So everywhere there's an s now, it's going to be an s minus 2. So this is going to be equal to, s minus 2 all over s minus 2 squared plus 49. All right, so the inverse form says that the Laplace inverse of capital F of s minus a is going to be equal to e to the at f of t. So really just, doing the previous theorem in reverse. So what we're going to do is we're going to evaluate the Laplace inverses of these 2 functions. So very similarly to what we did when we found the Laplace inverse before is we kind of treat something like that's factorable denominator as, partial fractions. So let's clean this up. I know that 3s plus 2 all over s minus 4 squared can be written as some a all over s minus 4 squared plus some b all over s minus 4. So again, if I was going to ask you to integrate something like this is how we'd have to do this. So multiply both sides by the least common denominator. We're going to have 3s plus 2 is going to be equal to a plus b times s minus 4. And then expanding. Now I know for these things to be equal to each other, the coefficients have to match. So b is going to have to be equal to 3. And then a minus 4b is going to have to be equal to 2. Now since b is 3, this is going to be a minus 12 is equal to 2. So a is going to be equal to minus 40 plus 12. All right, so now I know what a is and I know what b is. So let's just rewrite this. So a is going to be equal to 14. B is going to be equal to 3. So let's erase this work here and then go ahead and find the Laplace. So now we're asking for the Laplace inverse of 14 all over s minus 4 squared plus 3 all over s minus 4. Now remember that's linear, so I'm going to Laplace inverse this and then also this separately. Now this one right here looks like, well, let's pull that out. Maybe I can make this look a little more obvious. This one I can tell is a transformation, that this is equal to, this is just like the Laplace of 1 over s squared. This looks like the Laplace inverse of 1 over s squared, except this is evaluated at s minus 4, which really means that we have that, that e to the 4 t in front. So this is, evaluated at s minus 4. So that means this is going to be equal to 14 e to the 4t. That's going to take care of this transformation, this shift, this s minus 4. And then the Laplace inverse of 1 over s squared is just going to be equal to t. So remember, this is equal to, Laplace inverse of this is just equal to t. So this is not a, well, I guess you can still think of it as a shift, but this, this would just be 1. But we know that this is going to be s minus 4, so this is just going to be e to the 4t. So this is plus 3 e to the 4t. Now for this one's a little more complicated. We're going to have to mess with this denominator and complete the square. The reason why I know is so far it doesn't factor. This is a factorable denominator and this one is not. So when they're not factorable into your real roots, what you're going to do is you're going to complete the square. So then it looks like either a sine or a cosine function. So I'm going to have a sum of squares. So let's work on that. So I'll do it over here. So if I have s squared plus 4s plus 6, what I know is in order to complete the square, I have to take half of that coefficient and square it. So 2 squared is going to be equal to 4. So what I'm going to do is I'm going to add 4, and then I'm going to subtract 4 to balance it, and we know that that right there is a perfect square. So I can rewrite this as s plus 2 quantity squared, and then minus 4 plus 6 is going to be 2. So that's this new denominator. Now, for me to simplify this, we know that we have something of the form now, the Laplace inverse of s plus 2 squared plus 2. Now, this has an s in it, and this is a constant. So I know the ones that have s's are your cosines, and the ones that are constants are going to be your sines. So I'm going to have to break this apart. But for the translation theorem to work, I can't have an s above here. I need it to share the exact same s plus 2 inside here. I know that this is a shift left 2, so I need the top to also have like an s minus 2 in front of it. And then this is going to have to be plus some constant. Now there's likely going to have to be some coefficient that lives in front of here. So that's kind of the goal, is I need to write this in this form so that I can take this a times s plus 2 over the denominator, and then plus this b over this. So let me write that to make sure that you understand what I'm trying to pull off here. So what I want is I want something like this. The reason why I want that is because now this is in the form of a cosine, and now this is in the form of a sine. So we're gonna have to clean that up. Let's make this work. So if I have this s over 2 plus 5/3, what I can do is I can factor out that 1/2, and I'm going to have s plus 5/3. Now I want to introduce an s plus 2, so I'm going to add 2 inside here. But very similar to the way I complete the squares, I can subtract 2 to balance this thing, and I have a plus 5/3. Now I only want the s plus 2, so I'm going to leave the s plus 2 in parentheses alone, but then I'm going to distribute this 1/2 here. So 1/2 times negative 2 is going to be minus 1 plus 5/3. And now I can add these coefficients, so minus 3/3 plus 5/3 is going to be 2/3. So what I can see is that my a was going to be 1/2 and my b was going to be 2/3. So this is going to be 1/2 and this is going to be 2/3, which makes this 1/2 and this 2/3. Okay, so for cosine, this 1/2 can't be here. So I'm going to have 1/2 times the Laplace inverse of s plus 2 all over s plus 2 squared plus 2. That's a bad bracket. There we go. Plus 2/3 times the Laplace inverse of 1 all over s plus 2 squared plus 2. Okay. This one's good. You know, this immediately is that cosine. Remember, this is going to be shifted, so I'm going to have that e to the minus 2t. Now, this one's not so much. Remember that whatever's here, its square root has to be in the numerator. So if I have a 2 down here, what I'm going to need is I'm going to need a root 2 up here. Now, if I multiply the top by root 2, I'm also going to have to multiply the bottom by root 2. All right, so now we're pretty good on. So this is going to be equal to 1/2. Remember that this is the cosine of t. Sorry, the cosine of root 2t. But it's going to have to be shifted, so that shift is going to be e to the minus 2t times the cosine of root 2t. Again, this thing takes care of that shift, this e, and the root 2 came from the square root of this 2. And then very similar here, this is going to be, I could clean that up, but I'm going to leave it like this right now. I don't really care about rationalizing the denominator. That's not where we are. Again, this is a shift of the sine function, so I'm going to have an e to the minus 2t. That takes care of this s plus 2. And then this function here is going to be equal to the sine of, that square root of 2t. All right, well, I want to solve this differential equation, and what I can tell is there's a shift here because I have this e to the 2t in front of this t cubed. So this is going to have to use that translation theorem. So the first thing we're going to have to do is we're going to have to Laplace both sides of this thing. So Laplace this y double prime minus 4y prime plus 4y. And then we're also going to have to Laplace this side. I'm going to write this as e to the 2t times t cubed. All right, so when I Laplace this, we know that the Laplace of y double prime is s squared times capital F of s minus s times y of 0 minus y prime of 0. Now, minus 4 times the Laplace of y prime is going to be s capital F of s minus y of 0. And plus the Laplace of y is going to be 4 just times capital F of s. And now what we know is Laplace of this, well, remember that we know the Laplace of t cubed, that the Laplace of t cubed is going to be equal to 3 factorial all over s to the 4th power. So what I know is that this e function actually just shifts this thing to the right 2 units. So this is going to be equal to 3 factorial all over s minus 2 to the 4th power. Which we know 3 factorial is 6. So cleaning this up. Using the initial conditions, I picked some easy ones because it's really about, this transformation. So y of 0 is 0, y prime of 0 is 0, y of 0 is 0. So what I'm going to have here is factored out my capital F of s. We're going to have s squared minus 4s plus 4 is equal to this 6 all over s minus 2 to the 4th power. Now we know that this actually is s minus 2 times s minus 2. This is s minus 2 quantity squared. So when I send that to the denominator, we're going to have capital F of s is going to be equal to 6 all over s minus 2, actually to the 6th power. Now our last job, we Laplace it to make it algebraic. We solve it for capital F of s. And then once we Laplace inverse this thing, we are done. This is going to be the solution. So Laplace inverse of capital F of s is going to equal to Laplace inverse of this other side. Okay, well, in order for us to do this, what we're going to need is, this side is obvious. This is just going to be f of t. This is our solution, or y of t, whatever you want to call this. Call it y if you want. But this side, we know we're going to have to factor out this 6. And we know that, I'll put it this way. This is going to be the Laplace inverse of, we'll get to what we need here. This is 1 all over s minus 2 to the 6th power. Now I know that that is nothing more than a shift. So this is going to give us that e to the 2t. That's what that shift does. But really what we need to know is, what is a Laplace inverse of, s to the 6 on the bottom? Well, if I have an s to the 6 on the bottom, what I'm going to need is I'm going to need the power that is 1 factorial less. Very similar to this. If this is a 4 down here, this needs to be a 3 factorial on top. So 6 down here, this has to be a 5 factorial on top. So I'm going to need a 5 factorial on top. So if I put a 5 factorial up here, I'm also going to have to divide over here by, 5 factorial. If I multiply the top by 5 factorial, I have to divide the bottom by 5 factorial. So this is just multiplied by 1. It's linear. You can pull it in and out. So we know that this is going to be 6 over 120. 6 over 120. E to the, remember what this thing is that this is going to be, this was t cubed, which came from an s to the 4th, so this is going to be t to the 5th. So this is multiplied by t to the 5th. If you like our videos and you want to see more of this, don't hesitate to ask. Please like, subscribe, and share. Thank you.